Hello guys, so far we have seen what is angular displacement, angular velocity, angular acceleration, then centripetal acceleration, centripetal force, and then banking of rods. Banking of rods has, it's one application of circular motion. Now today we are going to talk about this vertical circular motion. What is the difference between vertical circular motion and uniform circular motion? The difference is in UCM, what you have is uh, the linear speed of the particle performing uniform circular motion, that is constant, right? It doesn't change at any point of time. But then when we consider vertical circular motion, the speed is not same at all points. Let us now see what it is. Now, let us have this particle performing vertical circular motion, right? Now, this is the center of circle. Let us call it O. Let us imagine that this particle, so this stone tied to a string moves in this vertical circle. Now, as it moves, it is going to reach some maximum height here, some minimum height here, and maybe any position, any intermediate position for that matter. Here I am taking midway position, correct? Now the angular velocity here. Now angular velocity. See, listen. One thing is there here. Okay, as the stone moves in the upward direction, like it crosses this point and moves here. Okay, the gravity is going to pull it down, so its linear speed is going to decrease, and it crosses this point here. Okay, let us call this point A, point B, and point C. So when it crosses point A, now the gravity is acting down, the stone is moving down, and even the velocity is in the downward direction here, correct? So from point A onwards to point B, the velocity will go on increasing, and from point B to point C and then to point A, it is going to decrease, correct? So let us now see, assume that velocity over here, linear velocity over here is, let us say it is V1, over here it is V2, and over here let it be V3. Radius of circle is R. M is the mass. Now this string, so now it is the string is going to have tension, but then the tension over here, the tension in the string when the mass is over here, the tension in the string when the mass is over here, it is going to be different, right? So let us mark the tensions. This is the center, and tension will be directed towards the center here, and weight of the mass, it is going to act in the downward direction. What about point B? At point B, the weight is going to act down. This tension, if I call T1, then this tension I will be calling T2. Correct? Now, since it is performing circular motion, there has to be certain centripetal force. So centripetal force at point A, it is going to be mv1 square upon r. So that centripetal force will be equal to the sum of tension and the weight. So m v1 square upon r is going to be equal to T1 plus mg at B, tension minus mg, and that is going to be equal to mv2 square upon r. Now let us consider one case. This mass, while in circular motion, its velocity v1 is such that it just crosses this point A. It just crosses, right? Velocity is just sufficient to make it reach this point A so that it doesn't fall down here. So in this case, what do you expect the tension to be? The tension in the string will be equal to 0, but then the string is not getting slack. The tension is just 0 and it is crossing this point A. So if I say T1 is equal to 0, then my mv1 square over r is going to be equal to mg. So if I cancel m on both sides, my v1 is going to be equal to root over rg. This is number 1. Now it crosses point A and then finally it reaches point B. Now here what do we expect the velocity v2 be? Now for that, what we can do is we can conserve the total energy. Total energy at point A should be equal to total energy at point B. So by that logic, now here if you take the lowest point B, because this mass cannot go any distance below below point B, right? So I'm taking B as my ground level. So potential energy at point A, it is going to be equal to R plus R, correct? So that is 2 mgr, right? 2 mgr plus its kinetic energy over there, and kinetic energy is equal to half into half mv1 square. But what is your v1? Your v1 is root over rg. So v1 square is going to be equal to rg, and half m rg, right? And that is going to be equal to the total energy at point B. And what is the total energy at point B? At point B, potential energy is equal to 0. Kinetic energy is equal to half m v2 square. So then again I cancel this m. So it is 2 gr plus half gr, that is, how much is that? It is 2.5. So that is 5 by 2 rg is equal to half v2 square, right? So my v2, now I am going to write here, I'll just cancel that 2 over there in the denominator, and my v2 will be equal to root over 5 rg. That is expression number 2. Alright, like we did here, we conserve the energy at point A and point B. We can do the same thing for point C here. Now what is the potential energy here? Potential energy is equal to, now this level, okay, it is at a distance r, correct? R from the bottom. So potential energy is going to be equal to mgr over there. So at C, and then kinetic energy is, if my velocity is v3, kinetic energy will be equal to half m v3 square plus my potential energy is equal to mgr, and that is going to be equal to total energy over here, and total energy over there was equal to half m into v2 square is 5 rg. Again I am cancelling m and m here, correct? Therefore my v3 square is equal to half v3 square. So v3 square upon 2 is equal to 5 by 2 Rg minus Rg. So 5 by 2 minus 1, so that is 3 by 2 Rg. Correct. So my V3 is going to be equal to root over 3 Rg. This is my expression number 3. Now you must have seen that we have taken only the topmost position, the bottom position and midway position. Is it possible to calculate the velocity at any point? The point can be somewhere here also. So how do we do this? Now here what we can do is, at this point the velocity is going to be tangential, we'll call it V. mg is going to be down and tension T would be in this direction, correct? And let this angle be theta, correct? Now this is one exercise for you to figure out what would be the expression for velocity at this point P. So that's about velocities at different points in vertical circular motion. In the next video we will continue with vertical circular motion, but then what we'll do over there is we'll try and find the difference in tensions at the topmost and bottom position. Thank you.